Rare minerals form when meteorites slam into the Earth, when there's an Earth impact. And how does that happen? Yesterday, we were told by scientists that the impact of celestial bodies on our Earth causes a decrease, a very huge decrease in the megasphere in the area of the Earth impact because of the plasma discharge. And now we have these rare minerals forming at impact sites. This is by Nick Timms on The Conversation. The discovery of a rare mineral, radite, at the Woodley meteorite impact structure in Western Australia was published by Curtin University honor students Morgan Cox and colleagues. Radite and other minerals are sometimes formed when meteorites impact our Earth. This takes a particular set of circumstances. Only 6 prior discoveries of radite had ever been reported. And here's what happens when a meteorite slams into our Earth. Rocks from space. We have scars on Earth, Mars and the Moon. We have a lot of comet and asteroid impacts, meteorite impacts on Earth. Our planet is continuously bombarded by meteorites, rocks from space, and has been since its formation about 4.5 billion years ago. These objects include rocky and metallic asteroids, comets, and other debris left over after the formation of our solar system, rock fragments ejected off planet surfaces from impact events, and potentially even rare visitors that have traveled from outside of our solar system. Space objects range in size from They're usually traveling towards us at velocities of many kilometers per second, that's tens of thousands of miles an hour, and this is so-called hypervelocities. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box. Fortunately for us, though, small rocks are the most common impacting our Earth's atmosphere, and Earth's atmosphere simultaneously slows them down, burns them away, and breaks them up. We can often see this happening as fireballs or shooting stars and meteor showers. Any surviving chunk of rock free fall to the Earth's surface could be collected as meteorites. The Fireballs in the Sky team at Curtin University has an amazing network of cameras to track incoming fireballs and predict the final land location of meteorites and work out where in the solar system they actually did come from. They've made some great meteorite discoveries in this way. Some rocks never make the final landing. Some may also produce an airburst. That's what happened with the Chelyabinsk meteorite over Siberia. An atmospheric pressure wave that can cause damage, like what happened in Chelyabinsk, Russia in 2013. And here, an asteroid approximately 20 meters or 60 feet across, traveling at 19 kilometers per second, exploded about 30 kilometers above ground, causing a blast that was strong enough to blow out windows of buildings in 6 nearby cities. Too big to slow down. Some incoming rocks are too big for our atmosphere to burn up and slow down, and these are much more rare. Of course, they're dangerous. These slam into our Earth at hypervelocities, which imparts a huge amount of energy and causes impact craters. The size of an impact crater mainly depends on the dimensions, density, and speed of the meteorite. There are many known impact craters in Australia, such as the Wolf Creek in Kimberley and the Gosses Bluff near Alice Springs. We know of craters that are now buried under layers of recent sedimentary rocks, such as Woodley in Western Australia. Globally, around 190 impact craters, or their eroded remnants, have been discovered on Earth, a lot fewer than scientists predict should have formed over all of Earth's history. It's because the Earth's surface is quite a dynamic place, and processes of erosion and plate tectonics act to erase evidence of impact craters over time. We also have impact craters that are underwater. Let's remember that the impact that we had 66 million years ago in the Yucatan Peninsula, that was the extinction event of the dinosaurs, is underwater. So there are a lot that are underwater. Now, the surface of the Earth is dynamic process of erosion. Plate tectonics act to erase evidence of the impact craters over time. The known craters range in diameter from a few meters to a few hundred kilometers across, and range in age from a few thousand years to approximately 2 billion years. No impact craters have formed in recent history, so scientists rely on studying ancient craters in combination with laboratory experiments and computer simulations to figure out what happened during each such catastrophic event. Recent times, no, but we did have the Clovis comet impact craters that were about 14,000 years ago. That was the end of the Clovis culture. So is that recent? Is that ancient? It's not that recent. But we did have other impact craters, as scientists found by watching and examining Google Earth satellite images in the area of just south of Giza. And that caused, of course, also volcanic lava eruptions, and also in the area south of Syria. And they saw that from the Google images. Now, the one under Cairo was estimated to be about 5,000 years ago. So, going back to this, speed and pressure. Now, no impacts formed recent history, they said. Scientists rely on studying ancient craters in combination with laboratory experiments, computer simulations, to figure out what happens during such catastrophic events. It has to do with the speed and the pressure. HyperVelocity impact events puts the impactor, that is the rock arriving from space, and ground zero, quote unquote, target rocks under immense pressure, which propagates through the Earth as a shock wave faster than the speed of sound. So the whole Earth vibrates. This is not uncommon for the rocks to reach pressures in the tens or even hundreds of gigapascals, equivalent to 100 billion times the pressure of Earth's atmosphere. Even the fractions of a second that rock spends at these pressures, some minerals transform into new high-pressure minerals, I guess like diamonds and things like that. For example, graphite can form diamonds, and the mineral zircon can turn into rhyolite, as described in the new paper. As the shock wave passes, heat energy is produced by the release from high pressure. This can heat the rocks enough to melt, and in many cases even completely vaporize the meteorite and rocks at ground zero. Vaporize them. You can imagine. They disappear. Shock waves also cause a lot of damage to rocks. They may break into fragments and get ejected high into the atmosphere and even into space, leaving behind a bowl-shaped crater. Eventually, when they go into space, eventually they come back down at Earth as what? As superheated rocks, you can imagine. Eventually, the shock wave loses energy, so it slows down and becomes less destructive and ripples through the Earth as seismic waves similar to those emitted during an earthquake. Earth changed forever. In huge impact events like the one that caused extinction of the dinosaurs and the 180-kilometer across Chicxulub crater in the Gulf of Mexico in the Yucatan Peninsula, that's underwater. The center of the crater is pushed upwards to form a central peak or a ring. It is quite alarming to think that all of these things occurred within seconds to minutes of the impact and can leave long-lasting scars on Earth's surface, cause significant environmental effects, and even result in mass extinctions. So you can imagine these dinosaurs, a lot of them that have been found with, the little buttercups still in their stomachs or their mouths, frozen or intact. This can happen in seconds to minutes of the impact. Now, impact craters are relics of truly catastrophic events on Earth. Rare mineral formation is just one of the possible outcomes when rocks arrive from space. This is by The Conversation on phys.org. Please leave your comments, and thank you for your support.